It might seem a little bit weird to use wedges and dashes on a picture like this, but it's actually pretty conventional here to use wedges and dashes for, what are these called? Bridgehead carbons? Whatever. So yeah, you do have to show this, you have to put this hydrogen here on a dash. It's important that you put this hydrogen on a dash to show that it's going to end up trans to this methyl group.
I've never seen like a cycloheptene.
No. It would be dashed as well.
No. This would have a map. Wouldn't this have two things?
Now, if we think of the hydrogen here as pointing into the page, what's the geometry of this carbon here? Because it's an sp3. This must be tetrahedral, which means that they're not really drawing this realistically. You can't have 3 bonds all in the same plane. So actually, one of these is really a wedge. So what this is really telling us over here is that if this hydrogen here is on a dash, we should be thinking of this ring as being on a wedge.
So you want the hydrogens to come in super dashed because
There's a huge substituent pointing in front. Let's check that answer. Did we get that one right?
Yes.
Yep. Yeah. Okay. Now this is kind of unfair, or at least it's maybe a little unfair that they expect people to know this, but you have to understand this when people are drawing rings. A lot of the time when people draw rings, it's not convenient to draw all the wedges and dashes. Instead, they only draw the dashes for the substituents on the rings. So to back up for a second, they only drew the hydrogens here on dashes, because these were the substituents. But we have to know there has to be somebody on a wedge. Otherwise, it can't really be tetrahedral. Well, if the hydrogens are on the dash, it must be the ring that's on the wedge. So we have to treat the ring as if it was on a wedge, and it helps actually put that wedge in there. And that means there's a lot of steric hindrance in front. So the hydrogen here should be coming in from behind. Good?
For 30, would it be less exothermic because instead there's more strain, you don't need to apply as much heat?
No. Isn't there more bond strain, it's easier to break?
Yeah. So you don't need to apply as much heat because it's more easy to break?
What would be the product from this hydrogenation?
Just a square.
And from this one?
Cyclohexane. So the first one is more willing to break the double bond because it's in a lot of strain.
So which one do you think was more exothermic?
The second one.
This one's more exothermic? Which of these reactions do you think was happier to have happen?
Second one.
This was happier?
I would say the first one.
Why would the first one be happier?
Because it's more steric strain, so
Oh yeah,
it's closer to breaking. It's like breaking bonds, so it's closer to becoming.
This is the reaction that seems like it should be easier,
Yeah.
because we're getting rid of the strain. Well, the easy reaction tends to be the exothermic one.
Oh.
Remember, exothermic is good. It means it's producing lots of extra energy. We're going to have to think about that a little bit more carefully. But it looks like we're saying this is going to be exothermic. Now, there's a difficulty here, which is, you were saying that this would be happier because there's so much strain here, right? Because it's a four-membered ring. But this is a four-membered ring too.
But you broke a bond, so it's close.
But you haven't broken the four-membered ring. It's the four-membered ring that's messing us up. So let's analyze this a little bit more. What is the hybridization of this carbon?
sp2.
So what does it want to have as its bond angle?
120.
We have memorized that sp2 wants 120 bond angle, but what would its actual bond angle be in a four-membered ring?
109.
What would the actual bond angle be in a four-membered ring, just
Oh,
based on
90.
yeah, you can just see from looking at it that it's got to be 90. Now over here, what's the hybridization of this carbon?
sp3.
So what does it want its bond angle to be?
109.
What does an sp3 want to have as its bond angle?
Hydrogenation doesn't have 109.7.
109.5. Yeah. You have to just memorize that. You can't figure that out unless you're really good at geometry. So we just have to memorize that tetrahedral means 109.5. And what's the actual bond angle?
90.
So who's more strained, the product or the starting material?
Starting.
Yeah, so you guys were right, although maybe not quite for the reason that you thought. This is more strained because even though we haven't gotten rid of the four-membered ring, we've gotten the wanted angle closer to the actual angle. So the important thing here is that we changed the hybridization. So you wouldn't get full credit on this if this was an exam question unless you were talking about the effect of the hybridization on what we want the bond angle to be. This is really hard for people to come up with because they say, gee, I studied hybridization and bond angles back in the first couple of weeks. That can't possibly be relevant anymore. But we have to apply those techniques to these new problems that we're seeing here. So so it's not so much this is why are four-membered rings so unhappy? Because the actual bond angles are not very close to what they want the bond angles to be. But it's even worse for an sp2 than it is for an sp3. For an sp3, there's only about a 20-degree difference between the actual and what you want, but here there's a 30-degree difference. Okay, so that means that this actually is the favored reaction. This is a very favored reaction because we're getting much closer to a good bond angle. So yeah, this should be a very exothermic reaction over here. What about this down here?
It's
Well,
like a chair, so it's super stable.
it would be if it didn't have the double bond. It would be if it didn't have the double bond, but again, just by looking at this, you can see these angles. So what does this carbon want its angle to be?
120.
It wants 120 because it's still sp2, but you can see this is a lot closer to 120 than this was. This is a much bigger angle. So I don't know exactly how big this is. You can figure that out by doing a little geometry. But just by looking at it, you can see that this angle is much closer to 120 than this 90 degrees is over here. So because this is not that unhappy at the start, it's not going to be that eager to get hydrogenated over here. So yeah, this bottom reaction is not that enthusiastic. It's the top one. So for full credit here, there's actually a bunch of considerations you have to go through to really explain why the top reaction is more favored. And the favored reaction should be the exothermic one. They did give us that hint there asking for the bond angle strain. But the key for the bond angle strain here was to actually think about the hybridization. You should start trying to apply hybridization to problems now because this is the first time we've really been dealing with sp2 carbons, right?
That is the actual is 120.
Oh, it really is 120?
Yeah.
You just worked that out?
Yeah.
Oh, good, great. So then this would be very happy. In fact, in a sense, that would be happier than this then, because this wants 109.5. Okay. Yeah, I think you're right. It is 120. Okay.
There's a formula that I learned for that. I think it's probably the same thing you did.
I just split it up into
Just-
triangles. However many triangles there are, there's 4 triangles, so it's 4 times 180 is the
In
total.
like 6th grade, they
Ah.
taught us that if it's like, it's still
Right.
180 times 4, but it's, if you do n minus 2, where
Right.
n is the number of sides,
Right.
times 180, and then,
You still remember that?
yeah.
Huh? Nice.